Hello and welcome to today's Industry Insights. I'm Chloe Stephen. I'm joined today by Sophie Prebble, who is our marketing and comms. She is going to take your questions on Slido. And the Slido code you should be able to see on the front page there. And today we're joined by Mike Dutton, who's going to take us through his presentation.
Thanks, Sophie. Good afternoon, everyone, and welcome to this presentation on design considerations for non-structural elements, focusing on ceilings and partitions. I'm Mike from Comfortech. I'm the ceilings and walls product specialist. Through my role at Comfortech, I work with architects, designers, engineers, and contractors. So I experience a wide range of challenges from early design stage right through to on-site installation. So in today's presentation, we're going to highlight a few of these areas of importance and offer some guidance to hopefully help you on your future projects. So some of you might be asking, who are Comfortech? So Comfortech is the result of two locally owned and operated companies, being Tasman Insulation, or Pink Bats, and Forman Building Systems. So we united a couple of years back now. We've got about 170 years of experience, and we offer a wide range of tried and tested systems and solutions for our ceilings, partitions, acoustic, thermal insulation, and our passive fire product ranges. Questions can be asked via that Slido using that reference 2382349. So what are non-structural elements and why are they so important? Your non-structural elements are those elements within a building that are not considered to be part of either the primary or secondary structural systems. So a few examples of non-structural elements are your suspended ceilings, your mechanical services, ducting, pipework, your cable trays, and light non-load bearing partitions. So these items can make up a large percentage of a building, and so when they're correctly designed and installed, they can save a lot of time and money on the overall building cost and the building performance. As we've learned from major events in the past, when non-structural elements are either overlooked or not constructed to meet the building code, it can have devastating consequences. So just to run through what we're going to discuss today. So in regards to ceilings, we're going to cover off code compliance and producer statements, manufacturer's proprietary designs, really important slide on clearances, some ceiling types, some seismic restraint methods, and we've got some other considerations and a couple of common questions that I get asked. In terms of partitions, we're going to have a look at your componentry, manufacturer's design tables and their engineering services, why we need to design to wind pressure, a range of wall types with the pros and cons of each of those designs. So this will include your full height and partial height partitions, your acoustic, your staggered and your double stud walls, extra high walls, shelf loading, bulkheads, bridging members, and then openings and external framing. So to kick off with ceilings, when we think about ceilings, there are a few key questions that we need to ask ourselves. The main one being, what do we want out of our ceiling? Is acoustics the priority? Is the focus for it to be visually appealing? Does it need to be fire rated or just group rated? What materials do we want it to be made from? Plasterboard, metal, mineral fiber, timber. Does it have to be hygienic or non-magnetic for use in like hospitals or laboratories? And then how do we plan to access services above the ceiling? So you think that these are simple questions to be asking, but from my experience, you'd be surprised how often these get overlooked. All these questions point us in a direction where the correct technical advice and decisions need to be made. So once designed, a practical, code-compliant ceiling can be built on site. So in terms of code compliance, when we're thinking about designing non-structural elements, there are a number of building codes we need to reference to. So I realise we're a bit time constrained today, so to keep these ones short, NZS 1170 Part 5, which is your structural design actions for earthquake loads. This is the primary document used to assess and calculate seismic requirements for structural and non-structural elements. NZS 2785, which is your suspended ceilings design and installation. This covers materials, ceiling types, design requirements, and installation. NZS 4219 is your seismic performance of engineering systems and buildings. This specifies interaction between components. So this covers the seismic restraints of services. And then another one that we often forget about is NZS 4541, which is your automatic fire sprinkler systems. So this covers the design of fire systems, defines bracing requirements for sprinkler system and pipe work. And this is important when we're looking at clearances and plenum spaces. So producer statements, a really important part of what I get involved with. What's a producer statement and why do we need them? So your PS1 is your engineered design by chartered engineer. So this is issued pre-construction and will be used by the installer as a reference to build the ceiling or the partition. Your PS2 is a peer review by an independent or a chartered engineer. This is where a design has been done, and then if requested, is checked by another independent engineer. Your PS3 is your acknowledgement by your installer that the installation is as per the PS1 or as per the building code. This comes after on-site installation is complete. Your PS4 is where an independent engineer does an inspection and signs it off. So basically they come in and they check to make sure that the installation is correct as per the PS1. So the main question following on from this is, when do we actually need a PS1? So the simplest way to answer it is first port of call is to check with your local council. It does vary around the country. Some councils pretty much require a PS1 for every ceiling that's modified. Other councils are a little bit more lenient, and as long as you're showing compliance, so that can be via the use of a seismic estimator or manufacturer's design documents, they're happy with that. So it always, first place you check is your local council. So in terms of compliance from manufacturers and documentation to help us with that, manufacturers' design tables, they're a really useful source of information in instances where there's a less complicated solution required. So the standardized range of parameters for use with their systems, this can be for load capacities, seismic strength. They also assist independent engineers with information for specific engineered designs. So when we're looking at this type of information, it's really important that we make sure the information we find on the internet is actually correct. I've had a number of examples where engineers or architects have found information overseas from like .com, so it might be USA. And in our instance, we use Armstrong as one of our brands. Armstrong's a worldwide company. They found information from Armstrong in America. Someone did a design based off it. It came to us supplying the product, and I said, well, we can't actually supply that product. It's ex-America. This is the best that we can do in terms of what's available to us. It was different in terms of its seismic performance. So the design had to be redone, which cost a lot of time and money. Had a conversation been had early doors about, hey, I found this, is this actually correct? We could have alleviated most of those problems. So just something to think about, that's all. Your manufacturer and distributor seismic estimators, these are really useful tools to show compliance in simple ceiling designs. They have a standardized range of parameters for use with their systems and can be used for both grid and tile and concealed stud steel systems. So they're really easy to use, they're free to use. You basically punch a bunch of information into them. There's a set range of parameters. And 3 pages later, there's a bit of a printout and it tells you basically what you can and can't do in terms of your design. It's real basic. They are very conservative in terms of their design because there is limited information that's put into them. But they're a really handy tool for contractors, especially as a way of checking compliance on really small, simple ceiling designs. It's one little thing just to point out with these design estimators, that they can only be used for certain brands. You can't use one for all brands. There is slight performance difference in terms of connection strengths and pull-out strengths on materials. So they are brand specific, but they are free to use. So they're a really handy little tool. One other thing with these type of seismic estimators, they are not a PS1. It's really important to highlight that. They'll give you that's why they're called estimators. So if you hand this over to council to say, hey, this is my seismic design for my PS1, councils won't accept it. It's only a way of showing compliance. So in terms of respecting clearances, really important slide. This is one that I deal a lot with on site where we have clashes. So as we know, the plenum space is shared by all kinds of services and suspension systems for your ceilings. So in a seismic These elements must not touch in order to prevent overall failure and items falling, causing damage, injury, or loss of life. The amount of clearance required will depend on the type of service and whether or not they have been adequately restrained seismically. So these clearances can be found in NZS 4219, 2009. So that's where that drawing comes from and those clearances come from. Really important that we try and adhere to those. I know it's challenging on site, especially with retrofit, but you know, we do need to try and keep to those clearances as best as we can. It's also important to note that the maximum weight of any item with a potential fall of less than 3 meters, so it's not very far, is 7.5 kilos. So anything over that weight must be independently restrained back to the structure. So just continuing on with clearances, realise that service congestions are a real issue on site. In particular, concentrated areas like corridors, where we often see them being used as service highways. You know, we chuck all the services down the corridors to get them out of the brim. So a proactive approach and good coordination can help mitigate issues and delays on site. So a really good example, a couple of photos here of a large hospital project where a contractor called me asking for help as there was no access for their suspension hangers. So what had basically happened is the structural engineer had done the structural design. The seismic engineer was a different engineer. There'd been no allowance for bridging members or anything in the tender documents. So I come to site, and then suddenly all the ducting has been installed under the only structural beams that we can hang the ceiling from. There's also large ducting, which was 1,500 to 2 meters wide. We need our hangers every 1,200 millimeters for a ceiling. So the contractor had to go back, had to allow for bridging members. This added extra cost and time to that build. So again, by raising this early doors and having a look at it, and considering everybody that needs to work in that space, a lot of this could have been avoided. So ceiling systems, so your grid and tile. So this is the most common ceilings that we see go in. They consist of a main tee, which is suspended from the building structure every 1,200 millimeters, either by 2.5 mil wire or 5 mil rod. The cross tee is clipped into the main tee at the nominator centers, which is usually every 600 millimeters. You're effectively forming a ladder. Systems are either 24 millimeter or 15 mil wide. 24 is your most common. There's not a lot of seismic performance difference between the two. They're made of the same material. It's just that bottom leg that's different. So a couple of little tips. So for ease of install, main tees are best designed to run across the building. So in the opposite direction to the purlins, so that we get, a good connection points for our ceiling hangers. So in seismic calculations, the cross tee run, so where our cross tees, the length of our cross tee, that run is normally double the maximum main tee. So to give you an example, if our main tees can run 10 meters before we need a seismic gap, we can normally get 20 meters out of our cross tees. So ideally, you want your cross tees running the length of the building, which is generally longer. So yeah, grid and tile ceilings, so normally installed with either 2.5 mil wire or 5 mil rod. They can also be direct fixed via the use of a clip. Again, looking at clearances, we want 100 millimeters from the top of the ceiling grid to the underside of whatever is above it. The couple of slides ago, we showed that the clearances with the NZS 4219, it shows minimum of 50 millimeters. So that's for seismic. We want that, but ideally to get a tile in and out easily, we want it to be 100 millimeters. So continuing with ceiling systems, we're looking at concealed steel framings. This is really commonly installed throughout New Zealand. Consists of a top cross rail, a locking key, and a furring channel. There's different profiles of the top cross rails and the furring channels, which gives you a bit of design flexibility on site. So again, 2.5 mil wire or 5 mil rod can be used as the hanger. And most documents will show 5 mil rod, but yeah, you are able to use 2.5 mil wire. Pretty simple design, really. There's a range of parameters in the design guides that you can follow. If you move the furring channels closer together or the top cross rails closer together, you can generally hold more weight, if you've got thicker plasterboard or multiple layers of plasterboard. So I'm just going to quickly buzz through some common seismic restraint methods. So you flex and float. This is for grid and tile ceilings. This is the most common method. This is the simplest and the cheapest method to seismically restrain your ceiling. So effectively, we have two edges that are attached to the structure of the building. So ideally perimeter walls. And then we have two that are effectively floating. And when we say floating, what we mean is that we have a proprietary clip, and it allows for the main tees and the cross tees to slide laterally in and out without falling out. We don't want them splaying apart, which in that instance, ceiling tiles could fall out. So just highlighting with these two slides, it's really important that we have ceiling nogging. It's really, really important on the fixed edge that we have this. The reason for it is if we don't have it, it puts a lot more strain on the perimeter angle. So by having perimeter nogging, it allows the main tees, allows that seismic force to go through the wall angle and be transferred into the structural, either a partition or if it's an exterior wall, might be a concrete wall. It's really important that it happens. Couple of options there. You can use a proprietary clips that are commonly used in this application. We fix it to the main tee via the hole, so it doesn't allow it to slide. The benefit of that is you don't see a rivet from below. You can still use rivets. If you look at the diagram on the right there, it shows a rivet being used. Depending on what seismic forces are going through that ceiling, can often be a 4mm rivet, can often be 2 4mm rivets. Just depends on what those forces are. But it's really important to have that ceiling nogging on that fixed edge. Where we have a fixed edge with no ceiling nogging, which those you're thinking retrofit applications, what we need to do is we need to upgrade that perimeter wall angle, so that becomes a seismic wall angle. So it's basically a thicker material, and it allows it to be fixed to the existing studs. So whether they're at 600 centers or 400 centers, we fix it through there, and it just allows the seismic load to be transferred back to the wall. If we use a standard wall angle in this application, it can deflect because it's not strong. On the floating edge, we are all good. Just to use the standard studs and fix at 600 centers. Again, the reason being is it's not actually taking any lateral load. All that the floating edge is doing is it's stopping those main tees and cross tees from sliding out or splaying apart. So you'll see here, we've got a screw fitted through the slot, and that allows it to slide because it's loosely fitted. Plasterboard ceilings are much the same, actually. We've got a dedicated seismic track. So on the floating edge, on the fixed edge, we fix through the holes into the furring channels, and that locks it in place. And then we just allow a nominated gap, whether it's 10 or 15 millimeters from the plasterboard to the edge of the wall. Normally that's done, it's normally covered up and made look good by like a negative detail plasterboard angle. And the idea being is it just gives you a bit of tolerance and a bit of clearance in a seismic event, so the ceiling is not crashing into the wall. We can have plasterboard cracking, that's fine. Superficial stuff, we don't want it, the integrity of the sheet failing and then the sheet falling down. The floating edge, it looks exactly the same from below. You just notice on the right-hand side there that rather than fixing through the holes, we're fixing through the slot into the furring channel, which again, that allows the furring channel to slide without falling out. So the next method after fix and float, we go into seismic breaks. This is where we break one large ceiling up into either 2 or into 4, and that would be either via a break in the main tees or a break in the cross tees. In this application, we have the gap ideally in the center of the room, the seismic gap, and we fix to the perimeter. So the whole perimeter becomes fixed. The benefit of using proprietary clips in this application is you don't see any of it from below, so you don't get a big gap. Finally, back bracing, everyone's favorite. It works really well. However, it is expensive in terms of labor, in terms of install cost per brace. This is where the perimeter is fully floating and the main area of the ceiling is held back to the structure, whether it be concrete or whether it to be, a roof above. So in areas of high seismic activity, Wellington, down on the South Island, up in Hawke's Bay there, we do often see this required back bracing. And it does become a bit of a challenge in terms of when we're looking at clearances and plenum spaces. We've got back bracing we need to install. We obviously don't want that clashing with services. So your back bracing will look something like this. A couple of different options here. There's a proprietary bracket that is generally used. The benefit of this is you get a nice clean cut, a nice clean finish, whether it's attaching to either your main tees in a grid and tile ceiling, or your top cross rail or your fairing channel in a plasterboard ceiling. The other benefit of using proprietary brackets is that engineers know how strong they are. So when they're calculating where braces are required, they know exactly what those proprietary brackets can do. So there is a benefit to do it. It does speed up that install. You can attach braces directly to the grid or to the fairing channel. It just gets a bit meshy. It's a lot more work for the installer. So on the left-hand side, you can see that we have a vertical strut out of steel stud, and we have diagonal struts out of steel stud. So that gives you a lot of structural strength. However, we realize in tight plenum spaces, we often don't have that space, or if it's a really big plenum space, we can integrate the use of wire, 2.5mm wire. So that's really handy when plenum spaces are crammed. Wire is obviously, it's not as strong as steel stud. So often, we may have to have a couple of extra braces. And so that just needs to be factored into that design, but it's a really handy and useful tool that we can look to use where plenum spaces are either really big or are really crammed. So just some other considerations now. So we talked a little bit about early engagement. It's really important in terms of managing challenges in tight plenum spaces. A really good example of this was another hospital project I worked on, where the architect actually organised the structural engineer, the seismic engineer, the HVAC engineer was on there, and so the mechanical services. There was a couple of suppliers were on there in terms of just adding extra information on what was required for either their ceiling or their sprinkler, whatever it may have been. So this was all organised really early before any decisions were made on product. It was organised by the architect. The good thing that came out of it was the structural engineer was having to design some beams to support all the mechanical services. The non-structural engineer who was designing the seismic restraint, he was on that call as well. There was lots of engineering speak going on in terms of loads and parameters and capacities. The nuts and bolts, what came out of it was we were able to reduce the need for another structural member to hold the ceiling up. That was incorporated into the original structural beam that was being installed or designed for the mechanical services. So it reduced a lot of time in terms of labour. It reduced a lot of space that was required in the plenum space, so created openings. And overall, really, really good example of why that's such a good idea to do things like that. Tile selection is often forgotten about. So if you've got a lightweight ceiling tile, you can see here we've got some that are under 2 kilograms per square metre versus a heavy ceiling tile. Some of them are up to 9, 10, 11 kilograms per square metre. That's a big difference in load on a ceiling. If it's 1,000 square metre ceiling, that's an awful lot of weight. So if you're struggling with lots of braces being required, by using a lighter weight ceiling tile, that can often be a way to reduce the amount of braces required. Your wall designs, so partition designs, that's a really good way in terms of if you're struggling seismically with braces and what's required. By using a full height partition and breaking bigger rooms into smaller rooms, you can often reduce the need for back bracing. You may even be able to get away with a fixed and float design. So rather than, in this example, you can see rather than having one big large room, by using full height partitions, we're able to break that room to 3 smaller ones and then fix and float those ceilings. So it's a really good way. Wind uplift, this is another area that often gets forgotten about. We've all been into buildings where you go in through the lobby into a reception area and the old wind pressure comes in and we get the tiles flapping. It's really irritating for people that work in there, having tiles flap up and down all the time. So a couple of ways to alleviate that. One is to use a tile hold down clip. So that's just clipped onto the main or cross tees when they install the ceiling and just holds those ceiling tiles down. Another way, especially in higher wind zones, lobbies and stuff, we see these being used in like public transport hubs and in universities, is to use like a clip-in tile. So this is actually clipped into a carrier rail from below. So it basically locks it in place. The benefit of which you can just use a little, it's a little install tool, and it pops the tile out, releases the tabs, and the tile can be released. So if you need to get in there for services, they're fully accessible. But they're a really good way of alleviating wind uplift. Another one to consider that I've seen a lot of recently is with the exterior soffits and wind uplift. So in these applications, we will have a vertical strut. It's generally a steel stud to reduce that wind uplift. So the reason I've put it in here is I've noticed recently that a lot of manufacturers have been calling for a vapor barrier. So back in the day, you used to be able to use like a heavy duty galv coating on them, but manufacturers now are calling for the use of a vapor barrier. So just check if you are designing those exterior soffits. Often they do require the use of a vapor barrier just to prevent that corrosion. So a couple of other considerations to wrap up ceilings, really. Services attached to ceiling tiles. This is really important. I can't highlight this enough. Ceiling tiles are only designed to support their own weight. So for lightweight fixtures, so like downlights, smoke detectors, and speakers, it's often assumed that these can be supported by the ceiling tiles. We need to refer to ASNZS 2785. So section 423 in electrical services, it actually refers to the fact that you cannot install, these lightweight surfaces directly to ceiling tiles. What we need to do is we use a supporting some framing. So either a bit of plywood or a bit of MDF. We cut it the same size as the ceiling tile, and the idea being it transfers the load of that surface. So it transfers that weight of that speaker or the light back to the ceiling grid, and it's important it goes back onto the grid. So if we just attach it directly to ceiling tiles, those ceiling tiles can sag, and at worst, that surface could fall down, and that's, we don't want that. It's also really important that when we are attaching things to ceiling grid, that we utilize the back of the grid. We don't want to be attaching things to the bottom of the grid. We often see different ranges of products out there that are designed to be attached to the bottom of the ceiling grid, whether it be baffles or light fixtures. The problem with doing this is it can void manufacturer's warranties. And the reason for it is, depending what type of clip or what type of screw or what type of fixing it might be, it can either cut a rather large hole in the ceiling grid, and this is it needs to be structurally strong for seismic, or it can cause that grid to deflect, and we don't want that to happen. So any of these items either need to be supported directly back to the structure above, or they need to be supported by the back of the ceiling grid via way of a clip. So it's really important that we utilize that. So insulation above ceiling grid and tile ceilings. Again, this is something that's often overlooked with changes to H1 and the increased requirement for insulation. We're talking R5, R6, R7 now. That's pretty thick. It's pretty heavy. So it's really important to note that most manufacturers will have a maximum weight limit the ceiling tiles can basically withstand in terms of insulation. You can see an example here. It's 1.27 kilograms per square meter. So it's actually not a lot of insulation. It's equivalent to like R2.4 BIB. The reason for them putting a number on it is what can happen is if it's, especially the problems occur when insulation is like it's compressed between, say, the structure in the case of like a baffle stack for acoustic, or if it's a thermal insulation, it might be squished in between some ducting and the ceiling tile. The insulation wants to return to its nominal thickness. And the problem with that is the ducting is not going to move, so it puts all that pressure on the ceiling tile. It can cause those ceiling tiles to sag. So ideally, we want insulation. We want it at roof height if we can. We want it up in between those roof purlins, whether it be sitting on netting or on some strapping. We just want it up off that, off those ceiling tiles. If it is to be installed on ceiling tiles, again, we want to make sure that it's a BIB, so it's a 1200 millimeter wide product, a roll form product. The idea being is we roll it over the main tees, so they help to support that weight. If you put segment insulation on the back of a ceiling tile, all that weight is being held up by the ceiling tile. The grid's not actually holding anything. So just a couple of little things that I have seen in the past. So just to wrap up ceilings, a couple of common questions that I often get asked. So one, are your ceiling tiles fire rated? So in the past, there was a system on the market that said they had a fire rated grid and tile ceiling. That's no longer available. The reason being is it's so hard to maintain that integrity. You can imagine if someone comes in and lifts ceiling tiles to access services, if that ceiling tile is not installed correctly, there's your integrity of your fire rated ceiling. So ceiling tiles are group rated for smoke. Most of them are either Group 1, Group 1S. If it's a timber ceiling or a timber product, it might be like a Group 3. But yeah, most of the mineral fiber or metal products are either Group 1 or Group 1S, and that's really important to know. So if you need a fire rated ceiling, we need to be using either a plasterboard ceiling system or a non-combustible board system. And then there's a range of those out on the market. The other one I often get asked is, what is heavyweight grid? So in terms of ceiling grid, there's two parameters for heavyweight. So there's heavyweight in terms of its load holding capacities, and there is a couple of products on the market that are stronger. There's data center grids, and they are designed to hold like cable trays. So that's all load bearing product. Standard grid on the market, which is where I generally get asked about heavyweight grid, is in terms of seismic performance. So that's where, to be classed as heavyweight grid, it's an ASTM test, so E580 and E580M. What they basically do is they will test a ceiling grid for compression and tension. There's a range of tests that they do. They drop the low result and the high result. If the average of whatever is left is over 80 kilos for both compression and testing, it is classed as heavyweight grid. So a number of manufacturers don't actually advertise this, that it's classed as heavyweight. But if you've got any concerns, please reach out to your grid manufacturer. They should be able to provide you this information to say that it's classed as heavyweight. Engineers will generally use 80 kilograms as their benchmark when they're doing their seismic designs. So on to partitions now. Again, we need to ask ourselves, what's the purpose of the partition? Is it for acoustics? Does it need to be fire rated? Is it going to be taking that ceiling seismic loading? A shelf's going to be hung off it? What are services in the wall? And again, by thinking about what the intended purpose of that partition is, we can refine that selection down to offer the best solution for your design needs. So your common componentry, everyone should be familiar with these. So steel stud basically comes in a range of profiles and widths, anywhere from 50 to 150 mil wide, and engages from 0.5 BMT, which is your base metal thickness, to 1.5, which is your heavy duty jam studs. So each size and gauge of stud will provide different span and strength properties. Noggin tracks are used to keep the studs in line and stop it from twisting. So yeah, all manufacturers will have a table showing noggin requirements in their design guides. Again, the different type of deflection head track shown will allow for a range of wall types and head connections. So your manufacturer's span tables, we spoke about it earlier with ceilings. We have the same thing for partitions. Basically, we have a generic table with a set range of parameters on it. You can see here that if we're using 13 mil plasterboard at 600 millimeter centers, we're going to be designing the wall out of 51 mil 0.5 BMT, that our maximum wall height can be 3.195 meters high. That's the biggest, the highest we can build that wall out of that profile. I've highlighted here in yellow the internal design pressure, and this is where the catch is with these type of design tables. So this one it's got an internal design pressure of 0.25 kPa. So it's not actually very high. It's a very low wind zone. So if you are in an area where a high wind zone, we can't use that table. So back in the past, pretty much all construction was done off these design tables. Now there's a lot more scrutiny in terms of wind. So again, you're just referring back to that internal design pressure, that we can't use that in any other application. We can only use it where that 2.58 internal design pressure is used. So further off for that, why are we designing to wind pressure? So designing to internal partitions to allow for different wind pressures is something that has become more prevalent in the last few years. Previously, it was all seismic. There wasn't the focus that there is now on partitions. The reason for the change is now we're building up a lot more. We've got large towers, especially in Auckland, 50-story apartment buildings. And there's a big difference between what the wind pressure is on the ground floor versus what the internal wind pressure is going to be 50 stories up. You know, if you can imagine you're opening a sliding door or a window 50 stories up, there's an awful lot more wind that's going to be hitting your internal partitions, possibly causing those steel studs to deflect. So one way to, I suppose, to get a more specific design in terms of partitions. So we've got our standard design table. So the next step up from that is to use our manufacturers. And most manufacturers have an engineering team. So we can send them through a full set of plans with the information, with the location, and basically what they'll do is they'll design the partitions in terms of, they'll have a document. So this document will tell you the wall height, it'll tell you the stud size, what centers they need to be at, how many nogs they need to be, what your fixings need to be for each type of wall in your project. So this is a free service. It generally takes 1 to 2 weeks to get this design back. It's a really awesome tool. It really is. Installers love it because it gives them really clear guidance on what they need to price and then what they need to do to install. A lot of councils will accept this document as a way of showing compliance for partitions. So yeah, really handy service. It's free. So you reach out to us. We'll all engage with Studco in this instance. And they, yeah, it's 1 to 2 weeks, they'll come back with an engineered design. It's not a PS1, however. It's just the manufacturer's engineering design. So further on from manufacturer's designs, we've done this a few times now. We need a really detailed design, a really specific design. We can touch base with consulting engineers, and what they'll do is they'll look at wind zones for your specific location, and they'll give a far more detailed design based on that wind zone. So they have a calculator that has a reduction factor on it. You can see there on the right-hand side. It's just an advanced version of what the standard design tables are. The big advantage of using a consulting engineer to provide these type of details is it's much more detailed. So the CPI, that's your reduction factor. So it's basically 20, you know, in the top there, we can see there it's 0.2, which is 20% of the external wind pressure. And if it's 20% internally, then we can use that top table. If we look at the bottom there, it's 80% of the wind pressure from outside. We can see there that in terms of our span heights, we basically can build about half as high as what we could using the 20% reduction factor. So much more detail in these type of span tables, really useful for those large buildings. You've got to look at like warehouses are a great example of where really high wind pressure can come in. You've got large roller doors that get opened, trucks entering and exiting buildings. That's basically a giant wind tunnel. So, you know, if you're thinking about your roof, can deflect an awfully long way. Also your steel stud cans in terms of internal partitioning. So we don't see an awful lot of PS1 designs for partitions. Generally, it's ceiling related. There is a benefit of getting a PS1 for your partitions as part of that package. The main reason for doing it is that engineer, you know, they can allow in their partition design to take the seismic loading. They know exactly what it is. There's no grey area in terms of which engineer is responsible for what, or the seismic engineer for who's designing the ceiling. You know, they're not assuming that those partitions can take that load. If they're designing themselves, they know exactly what they need to allow for. So again, really handy tool, really good thing to be doing, and doing it early doors. So we're going to just touch on some wall types now. Again, pros and cons of both. Really important here in terms of partial height walls. So there's a number of benefits. The number one being partial height walls are really quick to install. So from an installer perspective, they're easy to install. They do require to be braced back to the structure above. We can't attach those partial heights walls to the ceiling. That's really important. So we need to allow for vertical deflection, and we obviously need to allow for that seismic. So it could be via the use of a proprietary bracket. Otherwise, we could be attaching those braces directly to the head track, and then obviously the structure above there. The main benefit of those partial height walls, those walls that terminate at ceiling height or just above ceiling height, we don't get a lot of interference with surfaces in the plenum space. Obviously, you're going to have braces in there, so that does need to be allowed for. But yeah, you do reduce the risk of clashes in those surface spaces. The downside to partial height partitions, I suppose, if there is one, is just acoustically they're not that great. So what you would need to allow for is that you'd need to use, in the case of a grid and tile ceiling, we'd want to be using a ceiling tile with a high CAC, so that's that sound blocking. We don't want that sound going up and over the wall. The big benefit for those partial height walls is if you are retro or future-proofing buildings going forward, which might be renovated in 5 years, might be a short-term tenancy. If you're using a partial height partition, you obviously take your wall down, you take the brace down, and then you pop some new ceiling tiles in because you haven't touched the ceiling grid at all, so we don't need to worry about trying to fix that up. So in terms of speed, it's a really good option. Your full height partitions, so these can either be partitions that go slab to slab or slab to structure, so it might be a roof. The big benefit is structurally they're strong. So when we're thinking of breaking up seismic ceilings and breaking up rooms, full height partitions are great. They're good acoustically because you obviously block that sound, so you can get away with having a lighter weight ceiling tile, so something with just a higher NRC, which is your sound absorption. We do need to factor in vertical deflection in terms of full height partitions, and as I say, that can either be by way of a deflection head track beneath a concrete slab or beneath a roof. With lightweight roofs, we just need to factor in the fact that the vertical deflection could be quite a lot. We were working on a job recently where we needed to allow 100 millimeters of vertical deflection because the roof, that's how much the roof was going to deflect. Normally it's around 20 millimeters is our vertical deflection. A couple of little tips in terms of full height partitions. If you can get away with having your partitions run full height, but you run your linings to just past ceiling height, so you get the structural strength out of the wall, you get fairly good acoustics, but again, you reduce the clashes because you're not having to line around surfaces and plenum spaces. There's also a way of reducing that cost from a labour perspective, because again, you're not trying to line around surfaces in that plenum space. Acoustic studs, we've all seen these. There's a range of the different profiles on the market. The idea with them is that, and due to their profile, is that when sound waves hit one side of that profile, they will follow the profile. So because they've got the little kinks in them, it effectively makes that steel stud profile longer, so that by the time that sound wave has hit the other side of the partition, it's lost a lot more of its energy. So it does reduce that sound transmission. Big benefit of these is the thickness. They're only a fairly, it's got a small footprint in terms of 92 mils. They're very good acoustically, but structurally they are limited as to how high we can build them. So that does need to be factored in because we don't use a noggin track with them. Your staggered stud walls, again, acoustically they're very good. Structurally they're very bad. We don't really like them as a distributor or a manufacturer because again, you're not building noggin track into it. You're only lining one side of that steel stud. So you are really limited to how high you can build with this type of wall. Double stud walls are brilliant acoustically. They're very good structurally in terms of because you can put noggin track into them. Great for hiding services in apartments. They are really good acoustically. The downside to them is obviously it's a larger footprint. Extra high walls. We've seen in the past that traditionally large walls, like the one in the photo here, which is about 12 meters high, 11.5, 12 meters high, normally would refer back to being built out of timber because main contractors are generally building these things. They can refer to 3604. However, you imagine trying to get about a 6x2, 12 meters long. A, you're not going to be able to find one. B, it would be extremely, extremely heavy. C, it would be really hard to keep it straight. So by using steel stud, has massive advantages over timber in this application. We got our engineer, so Stakeco's engineering got onto this. So there's a large range of noggins in that wall. This was a movie complex in Auckland. And yeah, I think they're about 11.5 meters long, 12 meters long. So really good option, steel stud. in terms of building these type of walls. Steel stud for shelf loading. Again, there's design parameters and the design guides that can be utilized. Steel stud's actually pretty strong in terms of how much load it can take. It's often forgotten about. Often people assume that, hey, I'm going to be hanging a bit of TV, I need to have lots of timber in there. Again, if you talk to us or talk to distributors or manufacturers, they will have parameters. They'll have engineering teams who can design that wall to take those loads. This is probably my favorite slide in terms of services and partitions. So this was a site that we visited late last year. A few examples of where services have come in. So plumbers have come in, or electricians, whoever they might be, have come in, and they've, you can see on the photo on the left-hand side, they've cut half the steel stud out. The only thing that's holding up that wall now is that sheet of plasterboard. So, we need to be aware of this. This happens all the time on site. We need to be having these conversations that you can't do that. You can't just cut a stud out and leave it. Middle one there, another example of where a shower rose is coming out. They've cut 3/4 of that stud out. So, okay, how do we remedy it? Either we put another steel stud in there, or we basically create an opening like a lintel. But again, we need to have these conversations so that it's not left to someone to try and come and fix it after someone's gone. The right-hand side there, you can see there's a pipe running through a steel stud. You can cut holes in steel stud, no issues with doing that. But again, there's parameters you need to follow. The other question is why don't we bring that pipe up in between the studs so we don't have to cut a big hole in it? So again, have those conversations early doors. If this kind of stuff's going to be involved in your project, it's really important that these are highlighted so that someone doesn't have to come and try and fix it up otherwise. Bulkheads, I'm wary of time here, so we'll power on through. Bulkheads, ideally, great idea. The big challenge with bulkheads is when we're having clashes with services, often we need extra diagonal bracing or extra cross members to take ceiling seismic loads. If we've got curved bulkheads like the right-hand photo there, just due to the way they're constructed, they need extra diagonal bracing. So again, we need to be aware of those with clashes in plantar spaces. Bridging members, we touched on it earlier for ceilings. This can either be going below, say, HVAC ducting, or it can go up in between rafters, in between roof pylons to take ceiling framing or to take partitioning framing. So again, talk to our manufacturers. They will come up with engineered designs that shows, how to construct it, whether it be out of timber or steel stud, what brackets are required, and what size that needs to be. So again, really important that we talk about this so they can be factored in early. Otherwise, they get left, people tag out of them, and then someone's got to pay for it at the back end of the job as an extra or a variation. Just wrapping up partitions now, we've got our internal openings. So this is where the heavy-duty jam studs come in. Previously, we just use a standard steel stud, maybe have a bit of timber in there to stiffen it up or box that steel stud. What we're seeing now is a heavy-duty jam stud, so it's 1.5 BMT. It's also deeper, so about 60 mils deep rather than being sort of 40. There's proprietary heavy gauge brackets and fixings, brilliant for around doorways and around openings for windows because they've got that structural strength. So really good way to stiffen up a wall is to use this heavy duty stud. That same framing can be used for external non-load bearing partitions. So this is in between your portal frames. In Australia, steel stud is very commonly used in external framing. In New Zealand, we've traditionally, we default back to timber because primarily it's a main contractor doing these partitions. Steel stud has a number of benefits, especially when we're talking high-rise buildings in terms of non-combustibility. So it's a really good way of showing compliance and having a non-combustible product. Again, these are engineered designs where we get Stubco's engineers involved with this type of partitioning. So just to wrap up, really, references in terms of manufacturer design guides. These are a few examples of them. Each manufacturer will have them available. They should be on the manufacturers or your distributors' websites. They've got a range of standard parameters, design guides, install information. Really handy and useful tools for installers and for designers to get pretty straightforward information out of them. The AWCI, which is the Association of Wall and Ceiling Industries, which I'm part of, I've got a couple of code of practice booklets, really handy. One's for suspended ceilings and one is for partitions. The benefit of these is these are independent, so they're not brand specific. They give information in terms of compliance, and regulations, and then they've got a bunch of different details which shows common installation methods. Free to download on the AWCL website, really handy tools. And then finally for us, really, where to find information, jump on our website, BPIR information, so your building product information reports is on our website. Jump on there. There's data sheets, there's install information. If you jump on any of the manufacturers that we promote their products, again, if you need Green Star information, if you need warranty information, environmental information, generally it's all on those websites. You can reach out to me. We've got a live chat box on our website. I'm one of the people that look after it, so you can often end up talking to me. I can help you get that information. And then, yeah, finally, just our other CPDs. We've got one on as built, as designed, which is all around project management. So that's the benefit of that. So it touches on some of the stuff we've spoken about today, but primarily it's about design and different methodologies around design. We've got one on H1 and the changes to H1, which is our building for climate change. And then finally, we've got one on passive fire protection. So if any of those are of interest to any of the members, please reach out. And that's us. I really appreciate everyone's time. Hopefully you've taken something good out of it. If you've got any questions, you can either raise them now or feel free to reach out to me directly. Thank you all for your time.
Awesome. Thank you so much, Mike. That was very insightful. We do have a few questions, but we are going to answer those via email after the session.
Yeah, we can send those through to you, Mike, and then we can put them up in the
Perfect.
when we put up the resources with the video so that everyone can see them afterwards. So we'll send them through to you after this, Mike.
Fantastic. Thank you so much.
And thank you everybody for joining us. Just a really quick reminder that our awards, our Building People Awards, has been extended, and you have until next Friday to get your entries in. So we hope to see you all enter. Thank you.